Hi everybody, Ryan Jackson, hope you're well. The topic today is going to be transformer configurations, 1000 volts and less. These are going to mainly be the ones that are covered in the National Electrical Code, although we'll get into a little bit of utility stuff as well. The focus here is going to be on systems that we use here in the United States. I'll mention some Canadian and European stuff as well, but the main emphasis is what we use here in the US. So we can break down transformers into a couple of general concepts. We have solidly grounded systems, and that's what most of us use. In fact, I would say that most electricians will actually never use anything but a solidly grounded system. So we have solidly grounded systems. We will talk about ungrounded systems and high impedance grounded systems, and then we'll also talk about some of the other oddities, zigzag grounding transformers, auto transformers, and things like that. But when it comes to the solidly grounded systems that we use here in the United States, certainly the most common, at least in residential, is the single-phase 3-wire system. That's what supplies your house. That's what we've all worked with, and many of us have installed. We also have a single-phase 2-wire system, which is pretty uncommon here in America, although if you find yourself in the UK, this is what you're going to be working with, a single-phase 2-wire system. We also have a 2-phase 5-wire system, and the odds are you've never seen one and you never will, unless you happen to be in Philadelphia or the outlying areas. I know there's a little bit of 2-phase 5-wire stuff in Connecticut and again around New Jersey. We'll talk about the 3-phase Y-connected 4-wire system, 12208, 277, 480, or for our Canadian friends, 347, 600, also a very, very common system. Less common, we have the 3-phase Delta-connected 4-wire, which is also called a high-leg Delta. And we have a 3-phase Delta-connected 3-wire system, which is a corner-grounded system. And we'll show you kind of how that works as well. So this is meant to be a basic introductory course. I know when I was a young electrician, the idea of, what's the difference between 230 and 240 volts? And I didn't understand if that was a different configuration or what that was, or 120 or 110 and all these different things. So we'll go over the voltages and the transformer configurations for those that are new to the trade, or maybe for some of you guys that have never heard of things like a 2-phase system. This, of course, is what feeds your house if you're in the US. This is a 120/240 volt single phase 3-wire system, and it's called a single phase. It has one winding. Now, in most applications, you can use the number of windings as the number of phases. You can say, okay, it has one winding, that means it's a single phase, but that's not always accurate. The most accurate way to talk about phase is to bring in the concept of time. And quite frankly, it's a little bit more complex. It's a lot more complex than I want to go over in this video. So if you don't mind me just kind of saying this is a single phase, there is one phase. It's not phase A and phase B, because it's only one phase. It can't possibly be out of phase with itself because it's only one phase. So we're going to call this line 1 and line 2. And here in the States, we would have a neutral conductor connected to the middle part of the phase, and that gives us 240 volts line to line, 120 volts line to neutral. So this is probably the most common system in the United States. Here's an example of a single phase 3-wire transformer up in the air, and you can see 1, 2, 3 conductors coming off of it, one at each end of the winding and one right in the center. So there's our single phase 3-wire transformer. Much less common here in America, but very common indeed in Europe, we have a 2-wire single-phase system. We have an ungrounded conductor, and we have a grounded conductor. So it's just a matter of where you choose to ground the winding of the transformer. And remember, I've always really liked this symbol for a transformer because it's quite accurate. It is just a bunch of turns of conductor. So we're going to take one end of our coil of wire, and we're going to connect that to our load. The other end of the coil of wire will also connect to the load, but we're also going to connect it to the earth and the metal parts. That is a single-phase two-wire system. So this could be 120, or it could be 240, or if you were in Europe, you would see 230 line to grounded conductor. I don't have a good photograph of this system, again, because it is quite rare here in America. We've also got a three-phase, four-wire, Y-connected system, such as this, that you find in most commercial buildings. This could be 12208, it could be 277-480, or it could be 347-600. We've got three single-phase transformers connected in a Y pattern, so they all have one common connection point, and we're going to call that the neutral conductor. We're also going to take that common point and we're going to connect it both to the earth and to the metal parts of the installation. 120 degrees phase displacement. So we've got measured to the neutral. It would be the same, 120 from black to neutral, red to neutral, or blue to neutral. And it would be 208 volts measured from any two phases to each other. Now, where this can be puzzling for electricians is if I connect a line-to-line load, let's say a water heater, not three-phase, but line-to-line, that would be considered a single-phase load. Even though it's connected to two windings, we would call that a single-phase load. So that's where it gets confusing. We use the term phase in inconsistent ways in the electrical industry. So the reason I started this video is somebody had reached out to me and said, Ryan, you did a video and you talked about phases and lines, and what's the difference? And I said, you know, that's a really good point. I think a lot of people don't really understand the difference, and the main reason is because we use that term inconsistently. So there's our three-phase, four-wire, Y-connected system. And of course, this would be an example. We've all walked past this hundreds of times where we've got three single-phase transformers connected together in a Y with the common point connected to earth. And you can see the wire right down here. If you squint, that goes down and connects to the earth. And by the way it does that is there's a little copper disc, and it goes, actually it screws to the underside of the pole, and that connects it electrically to the dirt, and then this wire connects down to that little disc. So that's how we ground this system. So there you go, three-phase conductors, or three single-phase transformers connected in a Y configuration with the common point connected to the earth. Three-phase, four-wire Y. A much more unusual system is the two-phase, five-wire system. All this is two single-phase transformers. If we go back a few slides here, all I'm doing is I'm taking this transformer, single-phase, three-wire, right, 120/240. I'm taking this and another one just like it. I've got my single-phase transformer, and then I put another one across it. That's all it is. It's two single-phase, 120/240 volt transformers. And that's what it looks like. Again, you're only going to see this in Philadelphia or close to that area. If we look at the voltages, here I've got a single-phase transformer. I'm calling that phase A, or transformer A, and then line 1 and line 2. And of course, from A1 to A2, we're going to get 240 volts. Same thing with the other transformer that's installed vertically here. We go phase 2 or phase B, line 1, line 2. I would get 240 volts from B2 to B1. Now the neutral point is where all four phase conductors meet, and that's our fifth conductor. So again, it's a two-phase, five-wire system. Measured from A1 to the neutral, or A2 to the neutral, or B2 to the neutral, or B1 to the neutral, measured from anything to the neutral, we get 120 volts. And I think it's interesting, when you first start learning about transformers, is you can think of these in terms of voltage, or in terms of inches, or ounces, or whatever you want. It doesn't matter to me. But I always like to look at it in terms of length. If this is 244 inches, or feet, or meters, or whatever, and this also is 240 feet, then we know right in the center of it, it has to be 120, doesn't it? So what if I were to take my meter and connect it from B1 to A2? Well, I would have to do a bit of Pythagorean theorem. I would say, okay, I know two sides of a right triangle, and I'm trying to figure out the hypotenuse. So I would do the old a squared plus b squared equals c squared, and I'm not going to do the math here on the video, but I've got it here written in the corner. It would be 170 volts. Or, because these two lines are equal, I could just take one of them and multiply that by the square root of 2, and that would give me the same thing, 170 volts. So 170 volts from B1 to A2 or B1 to A1. Any A to B measurement is going to be 170 volts, and that is not a usable voltage. That's just a byproduct of the transformer configuration. That's just a mathematical construct. So it's not like you're going to be running out and buying 170 volt equipment. This is an example of a two-phase 5-wire installation. It's two conductors in parallel for each hot. So there I've got, let's call it A1 and A2, and then B1 and B2. There you go, and then we've got one neutral for each, two-phase 5-wire. We also have what we call a high leg system, which is a three-phase 4-wire delta connected system. Usually it's a 244 or 240 volt delta. So I have three single-phase transformers wired in a triangle configuration. Each of these windings is 240 volts, or again 240 feet, inches, whatever you want to call it, from here to here, and from here to here, and from line to line, everywhere we look. Therefore, we know if it's 240 volts, then the center of any of those points would be 120 volts, measured to the phase that's next to it. So here I've got, let's call this the B phase. I've grounded the center of the phase, taken it to earth, taken it to the metal parts, and created what we would call a neutral conductor. So from this point to this point, I'm going to have 120. And from this point to this point, I'll also have 120. And if I take any two phase conductors, any two ungrounded conductors, I'm going to get 240 volts. But then the question of the hour is, what's the voltage from this point up here down to the grounded portion? And that, again, we would figure out using the Pythagorean theorem. So if I were to draw an imaginary line here and figure out what the length is, I know that it's 120 and 240. So if I use the Pythagorean theorem to figure out what this is, we would find out that it's 208 volts. So there you go. There is the high leg system. Not as common today as it used to be. This is a high leg system. You'll notice that one transformer is actually larger than the others, and that's in terms of kVA, because one of them is going to get loaded has the potential of getting loaded up more than the other ones. So usually that's an indication that you have a high leg system. We're also required to do labeling anytime we have a high leg system. So this one, 240 volt delta, 3-phase, and this doesn't quite comply with the code. This should be a more proper label, but phase B is the high leg in this installation. So we've got 3 pole breakers, which is fine, because again, any 2 points, any 2 ungrounded conductors is going to measure 240, and if I'm using all 3, I wouldn't be using the neutral, so that also would be 240. You'll notice a single pole breaker up here, and it's on phase A. It is not on phase B. If it was on phase B, then we would be getting 208 volts out of it, and we'd be wiping out some equipment. So single pole breakers are fine on line 1 and line 3, phase A and phase C, but they're not allowed on phase B unless you jump through some ridiculous hoops that nobody ever would. Another thing that's important to consider is here we have a 2-pole breaker down in the bottom right, and that has some special requirements. That breaker has to be what's called slash rated, and what that means is if you look at a 2-pole breaker, it will either say 120/240, or it will just say 240. And on a normal system, 120/208, you could use a slash rated breaker, 120/240. But on a high leg system, if your breaker is on the high leg phase, it cannot be a slash rated breaker. It has to be just rated 240. Not 120/240, but just 240. this circuit breaker, I took this picture, was a violation. And most of the time that you see a 2-pole breaker on a high leg system, it will be a violation. If you don't ask for a straight rated 240 volt breaker, you're not going to get one. Now, when it comes to 3-pole breakers, I've never seen one that's slash rated, and I don't think they even manufacture slash rated 3-pole breakers. I think with a 3-pole breaker, they're all rated 240 or 480 or whatever would be the applicable voltage. The other type of delta that we commonly install is called a corner grounded delta. This would be a 3-phase, 3-wire delta connected system. It does not have a neutral conductor, but it does have a grounded conductor. So we have our 3 phases. We're going to take one of them. Usually it's the B phase, but it doesn't have to be. We're going to take one of those phases and we're going to connect it to the metal parts. And this is on the secondary. So we're going to take this point and we're going to connect it to the metal parts and to earth. And that's going to be a grounded conductor, which means it has to be white or gray. And that's a very common violation with corner grounded systems. A lot of times they don't feel comfortable having a phase conductor grounded, so they'll identify it with orange or something. Well, one of the problems with that is that it's a grounded conductor, so it's not allowed to be fused. And when people see an orange conductor in a disconnect, they often will fuse that conductor. So we're making it illegal by not having it gray or white. So this conductor is a grounded conductor, and it needs to be identified as such. You'll get 480 volts between any 2 phases, but from the grounded phase to the metal parts, you'll get 0 volts. And that's okay. That's why it's safe. You can walk up and touch the metal parts, and it's perfectly fine. There's nothing wrong with it. Every transformer that we install, basically, has a connection to the metal parts. It's just a function of where on the transformer do we connect it. Do you connect it at this point, or do you connect it at this point? Every transformer is connected to the metal parts other than ungrounded systems. So this is safe. You would read 480 volts between phase A and the metal parts and phase C and the metal parts, and you would read 0 from phase B to the metal parts. And some people say, well, geez, what if I'm touching the metal parts and I touch phase A at the same time? I'm going to get 480. Yeah, so don't do that. When's the last time you looked at a building and said, you know what I'm going to do? I'm going to grab the brown wire and touch the metal parts. Yeah, don't do that. That would be stupid, right? That's a good way to get yourself killed. This is no more dangerous than a Y-connected system. If you're touching the metal parts, don't grab an ungrounded conductor. Pretty simple. Here we have a picture. I'm not sure why these wires are so tight. I mean, it's like, geez, you can spring that extra $1.50 for an extra 6 inches of wire, But this is the secondary side, the blue, black, and white. And on the primary, we have yellow, brown, and orange. So this is a corner grounded system. We picked a phase, and as you can see, we connected it to the metal parts. This is done correctly with a white conductor. This one is done incorrectly with an orange conductor, and that's what most people do. So here we have orange on the secondary. We've connected it to the metal parts, and that is a violation. That is a grounded conductor, so that should be white or gray. There are a couple other delta configurations that we see, although usually it's not something that we install, it's something that we would receive from the utility. This is a delta. This is a 3-phase delta, and that's where people screw up. They see 2 windings and they want to say, well, that's a 2-phase system. Actually, it's not. This is a 3-phase delta, and it's called an open delta instead of a closed delta. So what will happen here is we can get 3-phase power out of this. This is a high leg open delta. If I connect a wire to this point and to this point and to that point, I can run a 3-phase load. So it is a 3-phase system. I also get 120 on those lines, and I get that dastardly 208 if I go up here. You'll always know when you see one of these in the field because you'll have two transformers, one of which is substantially larger than the other one because that one's going to be loaded up. That one has all of our 120 volt loads. So that one's going to have a lot more load than this one. So this one, and I hope I'm not making this up, but it appears that that says 25 and that says 100. I could be inventing this, but it wouldn't surprise me at all if that was kVA. 25 kVA and 100 kVA. We can do the same thing with a corner grounded system. We have an open delta, two windings, two single phase transformers connected like that, and that creates the same delta that we had. Instead of grounding it and creating a high leg, we would ground it and create a corner grounded delta. This is not a particularly useful configuration because it doesn't have a neutral conductor. It has a grounded conductor. You're not going to get 120 out of this. You're going to get 480, 480, and 480. So open deltas are used basically just to save money. You don't get as much capacity out of an open delta, but the utility doesn't have to pay for a third transformer. And here we have another example of an open delta. So when you're driving down the street and you see two transformers, you're probably not looking at a two-phase system. You're probably looking at an open delta. Then we get into the kind of odd configurations, and that would be a three-phase, three-wire delta, which is an ungrounded system, or a three-phase, three-wire Y-connected ungrounded system, very unusual. We also have high-impedance grounded neutral systems, grounding-type transformers, which are zigzag transformers, and we also have auto transformers. So taking these one at a time, here we have an ungrounded delta. 480 volts between any two phases. There is no connection between the transformer windings and the metal parts, or between the transformer windings and earth itself. That's why it's an ungrounded system. Now, all the metal parts of the installation are still connected to each other through an equipment grounding conductor. So this is wired the exact same way as any other delta as far as grounding and bonding is concerned. The only difference is at the transformer itself, I do not have that system bonding jumper that connects XO to the metal parts. And the connection to the earth goes straight to the transformer enclosure, but does not go to the XO point. It does not go to the windings. We can also do that in a Y configuration, although it's very unusual, and in the code, you're only in the National Electrical Code, you're only allowed to do this for 480. You could not do a 208 volt ungrounded system. You'll notice here that there is no neutral conductor on an ungrounded Y. If I need a neutral, I have to install a grounded system. So this is an ungrounded 480 volt Y. You should have ground detectors on an ungrounded system. Shockingly, that's only been required since 2005. But here we have our ground detectors, phase A, phase B, and phase C. And what it's doing here is it currently is showing us that we have a ground fault on phase C. That's why this lamp is glowing brighter than these other two. These are always on. And if one of them has a fault, one of the phase conductors has a fault, we need to know about that because the system will remain operational. But we will be getting, we will be stressing some motors during the ground fault because the motor windings are rated 277, and you get some stress on that. And then also, if you have another ground fault, you'll lose the system. The idea of an ungrounded system is to allow a ground fault to occur and not lose electrical continuity. So this burns brighter. It lets the electricians on site know that we have a problem and that we need to start doing some troubleshooting. That's, of course, is the inside of that ground detector. We also have a high impedance grounded neutral system, although I hate the name of that because there is no neutral. So it's a high impedance grounded neutral system. It's a Y connected system, and what we do here is we wire it just like a regular old transformer, just like any Y connected transformer, but in that wire that goes from XO to frame, we install a resistor. And usually in this application, this resistor might be somewhere around 277 ohms. Okay, and what that means is if one of these conductors has a fault to the metal parts, it has to go through a huge amount of resistance back to its source. So much resistance that it would never trip the circuit breaker. You think about it. If it's 277 volts from the metal parts to one of the phase conductors, and it has to travel through 277 ohms of resistance, that means only 1 amp of current is flowing. And that's not going to trip the breaker, which is what we want. Maybe this is a facility where losing power could result in the loss of life or something. So instead of tripping the breaker, it would set off an alarm like the ungrounded system that we looked at right here. We would have ground detectors. This is an example of the actual resistor itself right there being installed. Okay, what are we looking at here? This is a zigzag transformer, or a grounding type transformer. You would use this to create a grounded system from an ungrounded system. You would also use this if you had large amounts of harmonic distortion from triplet harmonics, so third order, sixth order, ninth order, etc. This is something that is typically done in a large scale. Like if you're doing a wind farm, you would maybe use a grounding type transformer. It's not something that we as electricians install very often, although it does happen. Now, if you have a grounded system upstream, then you cannot install a zigzag transformer, because that would be an illegal connection. So this is only to create a grounded system from an ungrounded system. The last thing that we have is what we call an auto transformer, and you can see from the drawing here that it works a little bit differently than a normal transformer. A normal transformer, I have one coil of wire, the primary, another coil of wire, the secondary, and I induce a voltage from the primary to the secondary. That's not the case with an auto transformer. I've got a 240 volt winding, and I want to step that voltage down incrementally, maybe down to 208 volts, because I have a 208 volt piece of equipment, but all I have is 240 volts. So I'm going to just count from here to here and get up to my 208 and make that connection right off the primary. You can do this to increase or decrease the voltage. Usually it's not by a huge percentage, maybe up to 20%. 240 to 208 and vice versa is probably the most common use for an auto transformer, although I have also seen 480 to 600. Sometimes we'll get a 600 volt rated motor, and that's the only 600 volt piece of equipment we have in the building. So instead of creating a whole new system with a transformer and disconnects and everything else, sometimes we'll go ahead and just use an auto transformer, step it up from 480 to 600. This is what an auto transformer looks like in the field. These two guys here are both auto transformers. The slang term for an auto transformer is a buck and boost transformer. All right, so that takes care of the transformer configurations that we use here in the States. I hope you enjoyed it. If you're interested in such things, head over to my website. You can get my changes book, my 2020 comprehensive guide to the NEC. Make sure you follow me on Instagram, Ryan Jackson Electrical. On Facebook, what do you do on Facebook? You follow. On Facebook, you like. On Instagram, you follow. And on YouTube, you subscribe. Okay, I'm getting this. Or you can just email me, ryanjackson618@gmail.com. If you ever have any questions that you'd like me to address, give me a shout out. Thanks, everybody. Hope you enjoyed it. See you next time.